Hello, my name is Jared Bolin, and this is my final project video on collision-free path optimization of 5-axis machine tools. Just a little bit of background. I want to describe volumetric error compensation, in which a laser tracker projects a beam onto a tool on the end of the machine tool. This allows the laser tracker to determine the location of the machine tool and any errors. So the optimization problem I'm looking at is between any two poses. If there is a collision caused between the laser beam and the machine components, I want to find an optimal path between these two poses that minimizes movement time and minimizes axis motion or energy. And the constraint would be no collision between the laser beam and the machine. So the importance, up to 200 to 400 measurements are required for volumetric error compensation, and it's very possible that you can get in a situation where a linear path in between two poses causes collision. Manually creating a plan that avoids this can take up to 2 or 3 days, adds cost and schedule, which limits the use of volumetric error compensation in production. I'm doing collision checking with a ray mesh intersection test. It's the molar trombone algorithm. Here over on the right you can see collisions in yellow between a start and a goal position, and the x-axis is c-axis position here, and the y-axis is a-axis position. And over on the left you can see a video showing in red where the collisions are. The optimization method that I'm using is the A-star algorithm. I'm searching the two rotary positions of the machine tool, the A and the C axis, and I'm continuing to use a linear movement for X, Y, and Z, which are all linear axes, and these are all linear as a function of the C axis. The A-star algorithm is an extension of Dijkstra's algorithm, with an added heuristic. As you move through the algorithm, basically you're changing the current node, and a node cost is computed. F equals G plus H. G is the start to node movement time in this case, and H is the heuristic. It's an estimated time between the current node and the goal node. The A-star graph you can see here completed on the left with the optimum path in orange. The blue is the closed set, the black is the open set, orange is the final path. Anything in yellow would be a collision. I do some bounded relaxation on the heuristic. This is called the admissibility heuristic. I add an E factor, which is a static weighting. Over on the left with E of 1, you can see it searches a very large space and takes quite a bit of time. Using E of 1.6 allows greatly reduced computation time, just a small penalty in the optimization. In this case, the movement time went up only by 1.5%, but I was able to search a much smaller space. And just to sum it up, here's a path comparison, a linear path on the left. You can see all the collisions shown in red, and then the optimized path on the bottom right. And on the top you can see the axis position as a function of time. So it took 10 seconds for the optimized path. That's it. Thank you.